when you're looking out at the horizon, you look around, and when you think about looking at Earth from space, you kind of see like this round curve, right? And it looks like a ball from space. And so when you're in the plane, you're pretty high up. You feel like you should expect to see like that kind of curvature, but you don't really see that much of it, if at all, right? It looks pretty flat. And when you're on the ground, it definitely looks flat, right? And so, for a while, that was always something that kind of confused me, and it's the main reason why people believe in flat Earth, and it's because, well, it looks pretty flat, right? There's no way the Earth is curved because look how flat it is. And when I've heard this argument, the thing that came to mind to me was like, well, maybe it's not that the Earth is flat, maybe it's just that like light bends. And I was like, well, there's no way that light bends like that, right? Because light shoots straight. You look at a laser, it's a pretty straight line. We use lasers to like make level surfaces and stuff. Like, it's pretty straight. So that doesn't sound quite right either. There's no way that that's the case. But then I found out about kind of how gravitational lensing works, right? And when we look at stars from far away, or, if you look at like the sun, when the sun gets blocked out, right, you can see stars that should be behind the sun because of gravitational lensing. The light kind of bends around the sun, and it seems like that shouldn't be something that it can do, but we know that it does, and it has to do with just how space-time works. And looking at this, I was like, that's really interesting. Well, we know gravitational lensing works with stars on long distances, but what if it works on Earth? What if that's what's happening on Earth? We have gravitational lensing on Earth. Because gravitational lensing is really just gravity. You don't even need the lensing term. It's just gravity. And that's what's really interesting here. And I'm going to show how. So imagine that you are standing, on the ground, and you throw a ball right straight out. You throw a ball really fast and it goes straight out. Now, what happens to this ball as it goes straight out? Well, we know, eventually it's going to fall back down to the ground, right? In our perspective, right, that was a curved path. That ball just took a curved trajectory. It went out and then it fell down slowly, right? But here's the thing. In the ball's perspective, it went straight that whole time. It never actually turned. And you may say, what do you mean it never actually turned? It obviously turned. It fell down to the ground. Now imagine a second scenario where instead of us throwing a ball, right, we have a river. And this river has a current flowing down, and it's pretty strong, right? On this side, we have, land. I'm drawing with stripes here. That's the land. And then inside where the arrows are, that's the river's current, right? So imagine we have a river flowing down, and we want to swim across this river or float across this river on a boat. We'll say we're floating across this river on a boat, right? This is my boat. It's not the best, but we want to float across this river on our boat, and we're going to row our way across, right? But if the current is pushing down, instead of taking this straight trajectory across, if we just row at a constant pace, and we're not rowing very fast, we're weak, all right? We can't row very quickly. What happens is if this current's really strong and we're rowing really slowly across this stream, what happens is we do make it across, but it really looks more something like that, where we got pushed down. Now, we never turned the boat. We kept rowing straight across the river the entire time. But what happened? We still ended up further downstream. Our path would appear to have bent, but we never actually turned. And so what's happening here is us floating across the river in the boat through the current is what is happening to the ball, because really what gravity is just this flow of it's this curvature of space-time, but really gravity acts like a current and pulls everything towards the center, right? And so the center of mass is always straight down from wherever you are. So, this is maybe not the best drawing here, but imagine, like, those are all arrows, and that's the Earth. So at any point on the Earth, wherever you are standing, straight down, that is going to be the direction of the current. And so when you throw a ball, right? If you throw a ball on the Earth here, or really any object of mass, you throw the ball. What happens is that we have this. Oh, goodness, we have this current pushing it down, and so as it goes, as it goes across, it falls down because the current has pushed it that way. But it went straight the whole time. It never changed its trajectory. And now, if you're understanding and you're following me so far, that is basically what happens with gravity. Because, imagine in a stream, we'll draw it on the side. No, we won't. We'll draw it all out again. Imagine in our river, right, we have, again, in our river, we put, we'll put our boat into the river, right? This is our boat. I'm going to put a little sail on it. We put our boat into the river, but we don't get in, right? And we just plop it in. Well, where is our boat going to go if we don't tie it down? It's just going to float straight downstream. It's never going to go across the stream because the current's just going to pull it down. And we're imagining a very straight current here. It's not going to bob and weave or anything like that. The river is perfectly straight, right? So where is this boat going? It's just going to go right downstream. Well, what happens when you don't throw the ball, right? And instead of throwing the ball, you just drop it. Well, where does it go? Right down, following the current. And so that is basically what gravity is. I think a better way to look at gravity is basically a current flowing. It's not to scale, but we look at this tree and when the light hits us, it's kind of bent like this, right? But when we're looking at it, like this line here, this line, right? This line that's really rough, but it looks flat. By the time it gets to our eyes, it's coming directly at us, right? So when we look out, the light that's hitting our eyes is coming at us at a direct angle. And so we perceive it as flat because when you look at these stars, right, that are behind the sun during a solar eclipse, you look at them and it doesn't look like the stars are coming from behind the sun. It looks like it's over that way, right? The sun is here, but it looks like the star is over there. But the star is not over there. The star is behind the sun. And it's because of this gravitational lensing thing. And so when we look at, something in the distance, what we're really looking at is not something that's in the distance straight out in front of us. It looks like it's straight out in front of us. And we can't perceive the curve because the only light that gets to our eyes is coming directly into our eyes. And so everything that comes directly into our eyes looks like it's straight out in front of us, which is really interesting because we can't see the curve. And I don't know. To me, that is really interesting. That is really fascinating, in my opinion, because an argument that's said often is the buildings should look like they're tilting away from us, right? But the thing is that it is. But here's the thing. You got to think about it like this. You're over here, the building's tilting away, but this light is bouncing off and then it's coming up. And by the time it gets here, right, now it's flat again. So we think that the building should look like it's tilting away from us, but basically everything is getting lifted up as you go out. And then the reason why we have the horizon is because at a certain point, all of these lines are piling up on top of each other. And so things that are too far away, these lines are kind of... So imagine things off in the distance like this, right? So we have these things here, but when these things, this light, the farther away it is, the longer it has to be affected by this gravitational lensing, so the more it gets pulled down. So something that should be farther away, what it's doing is the light is not reflecting straight off of it, because when you look at an object like the back of my hand, you can't see it, but it is reflecting light right now. And the top of my hand, you can't see it necessarily, but it is reflecting light right now. And so at a distance, the light that is bouncing off my hand and not going directly up, but is bouncing off and going out that way, right? That light that is bouncing off on an angle off of my hand, that's the light that is, traveling off and someone could see at a distance. The higher up we are, the higher up on the tree you are, the more straight out the angle is, or even down the angle is. But the lower you get, the light that you're seeing is actually the light that's getting shot up, not straight out. And if we were on, let's just draw like a ladder or something here. And when you're higher up, you notice like from higher up, you probably wouldn't see the trunk of that tree or at least some of that trunk, because what happens is that this light would have to travel like this, but it would hit the branches. So you don't see that part of the tree. You only see that top of the tree. And then at some point down here, then we would be able to see the tree again. And it's something like this. So when we look at a tree, we think, let's get another line in here. We'll get a different color. We think we're looking at the tree straight on. Right? And we imagine that the light that is hitting our eyes is coming straight on. But depending on how far away it is, that's not the case. Something close up like this, like me right in front of your face like this is pretty much straight on. But if I was 100 feet back or 100 meters back, right, I'm no longer going to be the light straight on at you. I mean, it's probably ever so slightly arced. I mean, 100 meters may not even be enough to necessarily get that serious drop-off, but it does happen at a distance. And we notice this happen, and when we look at things at a distance, like I said, at the horizon, all of these lines kind of converge together. They blend together. And I've seen this argument before where out on the ocean, right? We've got the ocean, we're looking out on the horizon, and you can sit there and watch a boat sail over the horizon if you have a good enough camera. And as the boat sails over the horizon, it disappears, right? So you got your boat on the horizon. And as you watch the boat sail over the horizon, it would probably be smaller than this. But you can then zoom in your camera, and then all of a sudden, voila, it's back. There it is. There's no curve. No, that's not what happened. What happened was that you zoomed in with your lens, and because you zoomed in with your lens, these lines of photons that were blending together, like the lines in between the photons, were so far away, the light became so far away that the line of the between these two, when they reached your eyes, was too thin for your eyes to actually see them. When you look at the horizon, the ship went from being this big to being this big, right? And now it looks like my hands are touching. But if you zoom in, right, if you zoomed in, all of a sudden my hands look like they're touching. But if you zoom in really close, all of a sudden my hands aren't that close anymore, right? And that is what's happening when you zoom in with the camera. And at some point, you could keep zooming in with the camera, keep zooming in the camera, following the ship, but eventually you will still watch it float out of view. And the reason for that is because of what I said. Because at some point, even your camera can't even make out that difference. And eventually, the light, if it's no longer that you can't make out that distance, the light eventually falls before you. And so in order for you to still see it, you have to keep moving towards it, because that light is only making it so far. As the ship floats away, the light is now not making it to your eyes, it's falling before you. So you have to keep following it in order to keep it inside your vision, because you have to keep those photons hitting where your eyes are. So you have to keep moving closer. And, or if you wanted to, you could go higher. And if you go higher, then photons that were going over your head are now in your line of sight. And these are, again, not the photons that are coming straight on, but are kind of shooting up and coming back down. But one thing I guess I do have to factor it in is the reason why we get perspective, things seem to get smaller in the distance. I was kind of thinking about this, and I'm like, how do our eyes know? How do our eyes know that something's far away? How can it tell, right? And the thing is the conclusion I came to is, well, technically your eyes can't tell. Your eyes just see what's there. The only way you can tell if something's really far away or just really tiny is with context. You need the whole picture to understand, because if you had just a white screen with a tiny boat, right? Would you know if that's just a tiny boat or really far away? You'd have no way of knowing if it was tiny or far away until someone put their hand right next to it and said, or put it in their hand and said, oh, it's a tiny boat, And so that's what I found that really interesting as well. And the thing is I thought, well, why is this happening? Well, why is it happening is because if you have your ball, right? Imagine at every given point on your red ball, red light is flying off your ball in every direction, right? And I'm not going to draw every line, because obviously if I did that, we would be here forever. But I'm going to draw a bunch in. And I want to just kind of point out the trend that is happening with these few lines. Now, if you notice, if my ball is shining light out in every direction, as these lines go straight out, as light does travel straight, but it bends because of gravity. Again, doesn't actually bend, it's just following the path of space-time, which space-time is actually bent. So a straight line around a ball, you could draw a straight line around a ball, but you're still going to kind of bend your finger around the ball, because the ball itself curves. And so space-time is the same way. But we don't even need to worry about that, because when we look at this here, right, we watch these lines go straight out, and as these lines go straight out, they are getting farther away from each other. And now this is very important, because now, when you're looking at an object, the farther away it goes, the less photons are reaching your eyes. And so an object that used to be made up by, trillions of photons hitting your eyes is now only getting made up by a fraction of that. And maybe that was an overstatement, maybe that was an understatement. I have no idea, because I don't really know how many photons are hitting my eyes at any given moment. It's probably a lot. But at a far distance, right, the amount of the photons of the initial object that hit your eyes is less and less. And because less of the photons are hitting your eyes, it appears to take up less of your view, right? And you can't tell why it's taking up less of your view unless there's other objects in play, right? So when you're looking down a street, you can tell, well, the street isn't actually getting tinier, right? It's just that it's farther and farther away. But you can't tell that without understanding the context of the photo, right? And so, in a photo, really, it's just getting tinier. But in real life, when you're looking at an object, it is farther away. But, this is why we kind of get this smaller and smaller perspective, and things get harder and harder to see at distances, because our eyes are having to make out an object from fewer and fewer photons, to a point that we just don't see it anymore, and it vanishes into a single point in the distance, because when we're looking straight out at something, the only photons that can reach us from straight out have to come directly towards our eyes. And at some point in the distance, there's either no photons that directly reach our eyes, or there's only like a few photons that are reaching our eyes, and it's not enough for us to make out what it is and define an object from it. It just looks like a blur, and that is, again, part of the horizon. So, yeah. Why does the Earth look flat? Because of gravity. Peace out.